Hello and welcome to part 3 of lecture 26. I apologize if you do hear some background noise. There's some other things going around in my house that I can't control the volume on, so hopefully you can filter that out as you listen to my lectures. Okay, so we've introduced what an inner product is. Now what we want to do is define what inner product space is. So basically a vector space that has an inner product is called an inner product space. So as an example, they exist, and we know that because, for example, f of n is an example of an inner product space. Right? Because we know that there's at least one inner product on this space, you can take the Euclidean inner product. So Fn is always an example of an inner product space. Now, what are some of the basic properties of an inner product space? Well, here's some of the properties that will be useful. First of all, if we fix a vector u in V, then the map that's given by going from the vector space to the field F, given by taking a vector V and sending it to V comma u, sending it to the inner product of V and u, is a linear map. Okay, so that's kind of nice that inner products kind of give us linear maps. So you're fixing the u, and then what you're doing is you're running through all the vectors v, and then you're forming the inner product, and you get something in out. So that gives you a linear map. 2 and 3 are basically saying the same thing, that whenever you take an inner product of an element with 0 as one of the vectors, you get 0 as your answer. Right? So this is true for any vector u in V. And then, right, in the definition, right, we only talked about what happens in the first slot. So what happens in the second slot? Well, it turns out you also can do the same sort of thing for the second slot. So the inner product of u and v plus w is the same thing as the inner product of u and v plus the inner product of u and w. So that gives you one property. And the same thing about the scalar, but here you have to pay a bit of attention to what's happening. Is you can pull out the scalar, but more than that, you have to pull out the scalar and take its conjugate. So this is the complex conjugate. Okay, so you can pull scalars out of the second coordinate, but if you pull it out of the second spot, you have to make sure you replace it with the complex conjugate. Okay, so I'll just give you, I won't prove all of them, but I will prove 4 just to give you a flavor of how these proofs are done. So let's say we want to prove 4. Okay, well, what we're interested in is kind of breaking up what's happening in the second spot, but our definition only allows us to break things up if it's in this first spot. So the idea is to flip things around so we can put things into the first slot, right? So we know by property 5 that this is the same thing as v plus w in the first slot and u in the second slot, and then take the conjugate. And then, because it's in the first slot, this is now equal to this, okay, because we have additivity in the first slot. Now these are two complex numbers, and you're taking its conjugate. So via the properties of complex numbers, this is the same thing as the conjugate of this number plus the conjugate of this number. And then you can flip them around again. That this is equal to uv plus uw. Okay, and that's all that we needed to prove, right? Because we wanted to show kind of that we had this additive property in the second spot. Okay, so let me put here some comment, right? So gives a flavor of the type of proofs when you're dealing with inner products. What we do is we flip around so we can look at the first coordinate. All right, because we're only, in our definition, we're only given properties about what happens in the first coordinate. So we take something that may be happening in the second coordinate, flip it around so we can put it into the first coordinate, and then we flip it back. And when we're flipping, we have to keep track of, the conjugate as we flip it back and forth. Okay, so now we can actually define the norm in orthogonality. Okay, so the norm of a vector is simply defined to be, so this is the notation, and it's defined to be the square root of the inner product of v with itself. So this gives me a number, and then I'm taking the square root of that. Okay, so as an example, we saw that this space had an inner product given by this formula. So we take the two polynomials and we multiply them together and we integrate from -1 to 1. So if we take any polynomial, the norm of that polynomial is defined to be the square root of the number that you get by integrating px squared on the interval -1 to 1, evaluating that integral, and then taking the square root. Okay, so this is another way of just writing the square root of the norm of p with itself. And then a term that you're probably familiar with from Math 1B03 is the idea about orthogonal. So remember from Math 1B03, two vectors were orthogonal if their dot product was 0, but the dot product is just an example of an inner product. So we can define this more generally to say that u and v are orthogonal if their inner product, is 0. Okay, so what we called orthogonal in Math 1B03 was just a special case of this particular definition. So in the last part, we're going to talk about some properties about the norm and orthogonality, and we'll end off with a proof of the Pythagorean theorem.